So we are starting our last section of this unit. We're going to have two lessons for 13.3, but we are coming up towards the end of this unit. So keeping that in mind. This is definitely a hard lesson. This is definitely a hard section. This is all about modeling. So taking relationships that we know of, geometry or other, in order to create equations and then use those equations to then apply calculus. So this is where it's all coming together, and it's going to be hard. So we have some strategies we're going to apply. We have some systems and procedures that we're going to put in place for every single time, because if we have systems and procedures that are in place for things that are difficult, it makes the difficult things seem less scary. So it's better to have those systems and fall back on those systems for when things start to feel a little stressful. So let's just first start with this guy. It says dimensions of a piece of A4 paper to the nearest centimeter are 21 by 30 centimeters. It is possible to create an open box by cutting out square corners and folding the remaining flaps up as shown in the diagram. This is something that we saw last year quite a bit. We saw it a few times. It was even on our test about this idea of creating a model that represents the volume from this situation. If you don't remember, that's totally fine. If you were not here with me last year, that's totally fine. We're going to re-explain it again. But this is the general idea that you have a piece of paper, a piece of A4 paper. If you cut squares out from each corner, you can then fold each of those flaps up and you create a box. So we're taking the dimensions that we know about for an A4 piece of paper and then an unknown idea of an x by x square to represent all of these behaviors that we're talking about. So it first says to calculate the maximum volume of the open box. So we want to make sure that when we're asked a question, we want to make a model that represents what we are trying to optimize. Optimize means to find the maximum or find the minimum, to make it the smallest or the largest. That's what it means by to optimize. We are trying to optimize what in this situation? We're trying to optimize volume. We're trying to find the maximum volume. So we need to create a model that represents volume. Okay. So we have a generic formula that represents volume. Go ahead and tell me what that is. Volume equals length times width times height, or base times width times height, or the three dimensions all multiplied together. But that is our generic model. Now we do have a situation here when we create a model, when we start with this model, when we start with most of our models in these types of situations, where the model has more than one input, right? We have a V as an output, but length and width and height are all different inputs. And we don't like having more than one input because we like to have it be a function of X. We like to only see one variable in our relationship. And so we need to make sure that when we're creating these equations, that we end up manipulating them in ways that make sure that they only have one input. Only have one input, which means we're looking for ways of substitution. Can we create other relationships? Can we create other equations? Can we create other equations or expressions that represent these dimensions as well as the one input that we want, right? So we want to be able to have not L here, but X. And we have an X, right? It's already established this diagram as having X. So how can we relate L and X? How can we create a relationship such that if I create an equation, I could then isolate for L in that equation and substitute in and then eliminate L and only focus on X? I'll say that again. We need to create an equation that represents a relationship between L and the input that we want, which I can tell from the fact that they're labeling something as X here, that they want us to make sure our input is X. I don't want L, I do want X, so I need to create a relationship that connects them. When I have, in other words, an equation that has both of them in it. When I have that relationship that connects them, I can then go through with my ideas of substitution, right? Isolate for one and plug in for the other to eliminate the L from the equation. So we say, okay, well, in terms of our box, length times width times height doesn't really matter which one is which, but I'll go ahead and label it that. So then going backwards from this idea, okay, well, if this is length and width and height, then that means that this must be length, this must be width, and then our height, notice, is when these corners fold up into the box, when those corners fold up into the box, it's created a corner, but really what it was before was just this dimension right here. These two corners fold up to create that corner of the box. In other words, this dimension is our height. This dimension is our height. So I can call any of these dimensions, because they're all squares of the same dimension, I'll call this as h. Okay, so we're trying to figure out from the diagram relationships. We're trying to figure out where length, width, and height are, and how do they then relate back to x. How does this guy as our width relate to x? And how does this guy as our length relate to x? I should put the w here. That's what I should have done. And then notice that our height here is just this dimension, which is just this dimension. And so our height is x. So that is one that we can figure out right away, which is pretty nice, that, oh, height is x, which is great. We could replace height with x, and we've already eliminated one of our inputs from this formula. Okay, now we need to create more relationships here that can help us out. We've seen like, okay, well, x plus w plus x equals that whole dimension, but we don't really have, like, you might be feeling stuck here on like, okay, well, what next? I see that they create this whole side. What else do I know? We've pulled as much information as we can from this diagram, but we haven't maybe looked at what's going on in this paragraph. So notice that it does tell us some information, numbers. Pay attention to the numbers. They're big. Highlight them. 21 by 30. So that means that this whole dimension is 30. And this whole dimension is 21. So we know that 21 equals x plus L. And we know that 30 equals x plus w plus x. So bringing all of these connections together, and with this idea of I need to create a relationship between the variables that I don't want with the variables that I do want. So that way I can start using substitution and eliminate variables that I don't want, can now lead us towards a way to create a model. So I can start putting it together. Where volume is equal to length, well, if I were to move 2x to the other side, length is just equal to 21 minus 2x. And then width, well, if I were to move 2x to the other side, and then height. So now we have a model that represents this situation where all of our inputs are gone, and now we have just one input, which is x, which is great because it's a function. It's something we can graph. It's something that we can maximize. It's something that we can minimize. It's got all of these things that are good, and that's our goal. Okay, so our goal then is to, well, our first goal was to make this equation. And then our next goal is to calculate the maximum volume of the open box, which means we need to take this guy and we need to maximize it. We're going to maximize it through calculus because that's what we're here to do. Is it the only way to maximize it? No, you could graph this and find the maximum point on your calculator, right? But we're going to focus on using calculus because that's what we're here to do. In order to find the derivative of this function, it would be nice if it was all multiplied out as one big thing, right? So multiplying 21 times 30, 21 times 2, 2 times 30, 2 times 2, and then multiplying x in there later as well. We need to expand this expression. I would like for you to go ahead and expand this expression. You end up getting, when you expand it all, 4x cubed minus 102x squared plus 630x, right? 21 times 30, 21 times negative 2x times 30, negative 2x times negative 2x. That's where your positive 4x, and then this would have been squared here. But then if you multiply x into all of those pieces that you get, you end up going up one more exponent.